Can everybody see that screen? It's just the bunch of pulleys and elastic logo.
Absolutely.
Okay, fantastic. All right, well, we'll get started. Thanks everybody for attending, and welcome to course number 4, which is part of the Optimising Pulley Lagging Performance series of webinars. And today we will be looking at identifying the potential for performance improvement. And we won't just be looking at performance improvement for the lagging, it'll be a combination of the lagging and its interaction with the conveyor belt. We'll look at the design stage when pulleys and pulley lagging are being selected, and we'll also look at existing conveyors and some typical problems that you can get on existing conveyors. The discussion will go for about 30 minutes, maybe 35 minutes, and then we'll have time for questions. If you've got any questions as we go, you can certainly raise them, or you can pop them in the chat, and we can deal with them at the end. But if you want to raise them while we're going, that's fine. So let's start with a look at drive pulleys in the design stage, where we're considering things like power transfer, localized slippage, inherent cyclic shear stresses that both the lagging and also the belt and the belt splicers have to deal with. And we'll have a look at the fatigue life of each of these components. We will also spend a little bit of time talking about how you choose the optimum ceramic tile coverage where ceramic lagging is being used. I don't know if you remember, any of you that were on course 2, we discussed the lagging select software, which is a tool that is used to identify causes of lagging failure, and it can also be used to help choose lagging that's going to perform the best. And the way that it does this, it looks at localized slippage and fatigue life. And for fatigue life, we look at 4 specific areas, and the areas we look at are the contact face. If you can see my cursor. So we look at the contact face, which is the this top surface of the lagging. We look at the tread root, which is at the base of the grooves of the lagging design. We look at the pulley shell interface. This is where this red line is. This is where the lagging's bonded to the pulley shell. And then we also look at the tile bond interface. And so what the calculations that we're doing today are going to do is look at the fatigue in each of those areas. So I'm just going to quickly run through about 12 different lagging types. It's actually 6 lagging types, and each one in 2 different thicknesses. We'll just look at some calculations, and at the end I'll put a summary up, and you'll be able to see the comparison and why we would make certain selection decisions. I think first we'll just have a quick look at what's called localized slippage. So let me... So localized slippage is quite different to full slippage. This is full slippage, so you've got slippage between the belt and the lagging around the full arc of contact. Localized slippage occurs just in the section prior to the belt leaving the lagging, and it's due to differences in the retraction. The belt, as it goes from T1 to T2, retracts, and when the lagging can't retract at the same speed, you get what we call localized slippage. Now, the analysis we're going to look at are all based on the same set of conveyor parameters. They're here on this little chart. So we've got T1 and T2. In this particular example, T1's 343 kilonewtons, T2's 96. So the ratio is quite high. We're going to be doing the analysis with a steel cord belt, ST1600, and a wrap angle, a pulley diameter of 1200 millimeters and a wrap angle of 210 degrees. The first lagging is 12 millimeter diamond rubber, which is a pretty standard lagging. This, just to explain this graph, on the left-hand side, the vertical axis is the normal pressure and shear stress. Across the bottom, we have the wrap position. So we go from 0 to 210 degrees. So this is the arc of contact. And then on the right-hand side, we have the friction factor. Now, the graph itself, this dotted red line is the dry coefficient of friction. The dotted green line is the wet coefficient of friction. This black line is the contact face pressure. So you can see it starts off high when the belt first contacts the pulley, and it drops off as you move towards the exit. The yellow line, sorry, the blue line is the shear stress, the developed shear stress. And this dark red line is the developed friction. Now, in this case, the developed friction comes up to this point where it intersects our dry friction factor. And what we're seeing here is that from this point on, which is at roughly 175 degrees around the arc of contact, we're actually getting slippage. So this is what we call localized slippage. So from 175 degrees round to 210 degrees, the belt and the lagging are slipping, which will obviously cause damage. And you can see down here in the calculations, it's saying that we've got 37 degrees of localized slip, which is 18% of the arc of contact. Now, the next slide is the same lagging, but in 25 mil thickness. What the extra thickness has done is it reduces the amount of slip. Now the slippage is only occurring from about 190 degrees around the wrap, around the arc of contact. So you can see down here, 19 degrees of localized slip, 9%. So the extra thickness makes the lagging more flexible, and so we've reduced the slippage. This next one is 12 mil diamond ceramic. So basically it's like the 12 mil rubber, but just with a single ceramic dimpled tile in each of the large diamonds. What we can see on the graph for localized slippage is that we've got about 14 degrees of localized slip. But now you can see there's a red section down the bottom, and we have a second graph. Now this second graph is looking at the fatigue. And just to go through how the graph's set up, the vertical axis on the vertical y-axis is the average shear stress. The horizontal x-axis is the normal pressure or shear stress. Again, the dotted red line is the dry coefficient friction, and the dotted green line is the wet friction coefficient. And then these coloured lines, the yellow coloured line is the fatigue limit at the pulley shell interface. And by fatigue limit, we've made some arbitrary decisions. So basically the fatigue limit's calculated on a pulley that's operating 60 RPM, 24 hours a day for 5 years. And we look at the characteristics of the rubber, and that gives us a certain number of cycles before we would expect the failure at that particular position. So we've got the yellow line for the pulley lagging shell interface. This orange line is the tread root limit. So the bottom of the grooves, that's the fatigue limit. And then the purple line is the tile bond limit. Now this black line is our operational conditions for this conveyor. So starting here On the right-hand side, that's where the belt is first contacting the pulley. So that's the inlet point, moving to the exit on the left-hand end of the black line. Now, the position of the black line being above the fatigue limit for pretty much all of these three things, what that's telling us is that the lagging would be expected to fail due to fatigue at those three locations some point before 5 years. We can't tell you exactly when, but it's basically saying, look, there is a problem there where we're going past the fatigue limit, and we wouldn't expect this lagging to last 5 years under these conditions. You can see up here in the graphical section where we've got things highlighted in red. What it's basically saying here is that the pulley shell shear stress is 156% of the fatigue limit, and the tile bond shear stress is 155% of the fatigue limit. So basically, it's just saying that we're not going to get our 5 years of life. Now, if we go to 25 mil thick, same lagging, just we've made it thicker. We still have a small amount of localized slip. It's come down to 7 degrees, so it's greatly reduced. And you can see down here on the fatigue side, we're now below the yellow line. The yellow line is the pulley shell interface, so we're not going to fatigue at that point. We are slightly above the tile fatigue limit in one area and slightly above the tread root limit, but it's better. It's better than it was for the 12 mil. So it's basically saying that we would expect the 25 mil lagging to last longer, albeit it may not reach 5 years. This is what we call a checkerboard ceramic. So it's 20% ceramic coverage and 12 mil. Our localized slip still exists. We've got 21 degrees of localized slip. We're not showing the second graph because we don't have any fatigue problems with this particular lagging. We now go to a 25 mil version of the same lagging. You can see that we have no localized slip. Localized slip has been eliminated. And also we have no fatigue issues. Now we'll look at what we call medium ceramic, or 38% ceramic coverage. So here we can see that we've got a lot of localized slip. The slippage is starting at around about 170 degrees around the arc of contact. So we've got roughly 40 degrees of localized slip. We have no fatigue. I should have mentioned earlier on these two numbers here, the minimum T2 tension to avoid localized slip, and also the maximum shear stress. The minimum T2 is a theoretical number that would allow you to, if we were, for example, to go from 96 kilonewtons T2 up to 162, this is telling us that this slip would be removed. The 193 kPa, the maximum shear stress that the lagging, between the lagging and the belt, this is an important number, because when we look at the end, when we have the table and we see all the results for the different lagging types, this will be one of the criteria that you would consider when you're making your selection. The lower if you can get no slip and no fatigue and keep the shear stress low, that's your ideal situation. This is just a 25 mil version of the 38% ceramic. Again, the increase in thickness to 25 mil has reduced the number of degrees of slip from 40 degrees to 21. There's no fatigue. You can see the maximum shear stress has also dropped because of the extra flexibility. And there's just two more, or one more version, which is the full ceramic. which is the 80%. This is quite a stiff and rigid ceramic. You can see here we've got the most localized slip of any of the laggings we've looked at. It's 54 degrees. And the maximum shear stress has gone up considerably to 206 kPa. But we do not have any, we don't have any fatigue issues. And then if we look just quickly at the 25mm version, extra thickness has reduced the localized slip from 54 degrees down to 33. It's also reduced the shear stress from 206 down to 143, and we don't have any fatigue issues. So just summarizing the results, and this is what we would do if we were trying to make a decision on what type of lagging to use. So we've got the different laggings across the top here: diamond rubber, diamond ceramic, the checkerboard ceramic, the medium ceramic, and the full ceramic. You can see here the ceramic coverage: 0, 15%, 20%, 38%, and 80%. And then here you can see the what we call the traction and the localized slippage. You see the levels of localized slippage. There is only one lagging that had no localized slip, which was this 25mm version of the checkerboard. And then these next 4 line items are the fatigue areas that we looked at. So the contact face, the tread root, the pulley shell, and the tile bond. The numbers are in red are where we're exceeding the fatigue life. So there were 2 laggings there where we had a problem with fatigue. And then these last 2 were the T2 to prevent slip, and then this bottom one, the maximum shear stress. So the thing that we're looking to do is we don't want any slip. We want to have the full fatigue life, so we're not going to get a failure due to fatigue. And then if we can get the lowest shear stress being applied to the belt, that's a good thing, because that'll help your belt splices last longer. So in this case, the 25mm checkerboard pattern is giving us the lowest shear stress, and it's also giving us no slip, and it's within the fatigue limits. So that's one of the ways that we can optimize and maybe take a bit of the guesswork out of how to decide on what type of lagging to choose for a particular application. I just want to quickly go through some rules of thumb on selecting or thinking about ceramic coverage. So in general, if you look at this little diagram, we've got a normal force that's applied by the belt onto the lagging and then onto the pulley shell. As our general rules of thumb, as the normal pressure that's being applied increases, and as the belt stiffness increases, then we should be looking at increased ceramic coverage. As the normal pressure reduces and the belt becomes more flexible, then we want to reduce our ceramic coverage and make the lagging more flexible so that it can move with the belt retracting. One of the other considerations as far as flexibility goes when it comes to lagging is the ability to soften point loads when you get material that's trapped between the pulley and the belt. If you have a flexible lagging, it's able to absorb some of that point loading. If you have a rigid lagging, for example, like direct bond's probably the worst case, or even hot cast polyurethane. Basically, any material that's trapped between the lagging and the belt has a very high point load on the belt and can cause belt damage. Sorry, I missed one there. So just general principles. More ceramic means that the lagging is less flexible, but more ceramic does make the lagging more resistant to wear. And then, for example, in this in the 80%, which you can see at the bottom, having more ceramic means that you can distribute the pressure more evenly. Now, this is quite an important consideration if you talk to belt manufacturers, particularly steel cord belt manufacturers, and if they're dealing with very high-powered conveyors, they're very concerned about the distribution of pressure. They don't want a lot of localized pressure or shear in between the cords of the belt, so they're very concerned about getting that shear force spread as evenly as possible. Let's have a quick look at non-drive pulleys on new conveyors. Quite often decisions are driven by the need to keep the cost of a new project to a minimum. Quite often that's done at the expense of what's going to happen once the conveyor is operating. So these recommendations that I'm going to go through now are really based on trying to get the best performance. So we're not considering the cost implications that are obviously quite important for new projects. We're just going to focus now on performance. So we're going to look at two things: resistance to wear, and also the ability to resist buildup. These photos show examples of the sort of wear that you can get on non-drive pulleys. The photo on the left and the photo in the center, these are from a turnover conveyor. And the photo on the right, this is from a conveyor operating with PVC solid woven belt that had stretched on the edges. The second criteria, apart from wear, that we're going to look at is build-up. And these photos show you some typical examples of build-up. These are all pulleys operating in contact with the dirty side of the belt. The one in the center is quite interesting. It's we don't see this in Australia, but it's a very common problem in Chile and Peru. This is on a conveyor that's handling ground ore that has been treated, ground copper ore. It's been treated with sulfuric acid. And this material is quite sticky. And what happens is it actually tends to attach itself to the ceramic tiles. And I don't know if you can see here, these little raised sections actually forms little pyramids. And they're as hard as stone. They're like teeth. It's like having teeth on the pulley. You can imagine what that does to the belt. So for resistance to wear, the common parameter that we use for evaluating that is called abrasion resistance, and the standard method of measuring abrasion resistance is what's called the rotating drum test method. There are a number of standards. ISO 4649 is one. There's an Australian standard called AS 1683, and there's also an ASTM standard. They're all very similar. Basically, the test machine has this drum. There's a small sample of the material that's being tested is put in this holder. It's weighed before it's put in. It's then lowered down with a fixed weight. This drum's covered in sandpaper, and the drum rotates, and this sample moves across the machine while the drum's rotating. There's a set number of rotations. At the end, the sample's taken out and weighed, and what you measure is the loss of material. So it's a bit unusual, because in this test, the smaller the result, the better the abrasion resistance. So a small number is good, big number is not good. When we look at resistance to build-up, there are two physical properties that affect this. The first is flexibility, In other words, the ability of the lagging to move and flex under load, because that makes it difficult to stick to. And then the surface energy or release characteristics. Low surface energy means that it's difficult for something to stick to. So low surface energy is things like PTFE or Teflon. We don't obviously use that in lagging, but polyurethane has quite low surface energy, and that's probably the lagging that has the best inherent release properties and resistance to build up. So this table is just a comparison for comparing, or for looking at the different types of laggings that are typically used on non-drive pulleys. So we have standard rubber lagging, we have polyurethane, we have extreme rubber. Extreme rubber is a rubber that has similar abrasion resistance to polyurethane, albeit at much lower hardness. It's 65 Giro compared to 85 for polyurethane. And then the last one that's commonly used on non-drives is plain direct bond ceramic lagging. So if we look at the properties, abrasion loss, standard rubber would typically be less than 90 millimeters cubed loss based on the test that we just looked at. Polyurethane would be less than 30, so a third. Extreme rubber less than 30, and ceramic would be less than 5. So the plain ceramic, direct bond ceramic, has by far and away the best abrasion resistance. But that doesn't mean it's suitable for every application. Hardness, standard rubber 65 plus or minus 5, polyurethane 85, so it's quite a bit harder. It feels like a plastic, it's quite rigid. Extreme rubber is 65, so it's flexible. Ceramic is very, very hard. When it comes to surface energy or the ability to release, we've just done a ranking of 1 to 4. Polyurethanes are 1, the 2 rubbers are 2, and the ceramic is the worst. And for those of you who've had experience with direct bond, one of the problems with using direct bond on non-drive pulleys that are in contact with the dirty side of the belt is the build-up. In Western Australia, I think BHP Iron Ore, Rio Tinto, and FMG are all moving away from direct bond on their non-drives because of build-up and because they've had problems with belt damage and also tracking. For the clean side of the belt, where you shouldn't have build-up as a problem, then that's where the direct bond is going to give you the best service life from a wear point of view, followed by the extreme rubber and the polyurethane, and then with the standard rubber coming in last. If we had to pick lagging for contact with the dirty side of the belt, polyurethane is probably the best, or extreme rubber, and direct bond we wouldn't use, and we wouldn't use standard rubber. So just in summary, if you were to use polyurethane or extreme rubber on these non-drive pulleys, typically the service life would be expected to be 3 to 5 times that of standard rubber. And although they are more expensive than standard rubber, that cost is very quickly recovered. So that's, we've covered most of the stuff on new conveyors. Let's have a quick look at performance improvement on existing conveyors. And whenever we look at existing conveyors, there's basically one question that we ask in relation to performance improvement, and that is the pulley lagging lasting as long as the bearings and the locking elements? So basically, if the pulley's having to be pulled out and refurbished, or the lagging's having to be replaced, and the bearings are still operational, then there's potentially an opportunity to improve the lagging performance. So I'm just going to quickly run through some of the common modes of failure for lagging, and then talk about what possible things can be done to minimize the chance of them. These photos, we're just focusing on debonding, edge lifting, and joint separation. And I'm going to put all of those together because effectively it's a breakdown of the bond between the lagging and the pulley. You can see this, the pulley on the right has been operating in very, very wet conditions, and you can see this corrosion and edge lifting. These, by the way, each one of these pulleys has cold bond lagging on it. The solution for eliminating this problem of separation of lagging from the shell is pretty simple. The bonding system needs to change to either hot vulcanized or to direct bond. And the reason those two systems eliminate the problem is they both have much higher bond strength. So cold vulcanized, you're typically talking about 12 newtons per millimeter. Hot vulcanized is typically double that, and direct bond is much higher than hot vulcanized. The next mode of failure that we will look at is tile loss, ceramic tile loss, and there are basically two types of tile loss. The one on the left, the photo on the left, is tile loss due to bonding system failure, and the photo on the right is tile loss due to operational conditions. By operational conditions, what I'm saying is that the forces that the ceramic tiles have been subjected to exceed the capability of the bond of the tiles into the lagging. The first one, the tile loss due to bonding system failure. This is by far and away the most common form of failure for ceramic lagging. It's identified by having neat, clean recesses in the rubber that exactly match the tile. So if you look down here, you can see there's little rectangular pockets, smooth at the back. This pulley here, you can see the little square indentations, smooth surface. Basically, when you see those pockets that are in the shape of the tile and a smooth surface, that tells you that the bonding system has broken down, and that's what's caused the tiles to fall out. Now, in every case, this is a manufacturing fault. You know, it's a manufacturing fault, and there are a bunch of reasons that can occur. If it can be the choice of the bonding materials that are used, it can be the method of coating, it can be the way the tiles are treated, it can be just the general process control. There's a whole myriad of things. Bonding's not easy. It's not an easy thing to do. But the way to overcome this is to always ask for a warranty on tile bond failures. There is, I should have mentioned, there is one circumstance where tiles can come out in a neat pocket and it's not a bonding failure, and that's when the lagging's subjected to excessive heat. So, you know, if you have consistent temperatures above 150 degrees C, or very high cyclic shear loads, very high powered conveyors, where you're generating a lot of heat due to hysteresis, that can actually cause a problem. But those circumstances are very, very rare. This is the second problem that we looked at, which is due to operational conditions. So this is where the tiles are literally being ripped out of the rubber backing due to excessive force. This photo on the left, this is a high tension bend pulley. Here the tiles are being ripped out because this pulley is contacting the dirty side of the belt. The belt is worn, and as a result, there are very high localized shear forces in the center. The way to minimize this problem or eliminate it is to use the lagging select program and look at the tile bond fatigue limit with the lagging selection. So the third common failure mode on existing conveyors is excessive wear. The pulley on the left and the pulley on the right, they're both rubber lagged pulleys, and the one in the center is a ceramic pulley. It's pretty unusual to get wear like that on ceramic, but we'll talk about why that can happen in a minute. The options you have for overcoming excess wear is you can go with a more abrasion resistant rubber. So for example, if you're using standard rubber lagging, you could go to the extreme rubber lagging, which has got 3 times more abrasion resistance. You can increase the lagging thickness. And the third thing you can do is you can go to something like polyurethane, which has both much better abrasion resistance, but it also has the low coefficient of friction. So in those photos that we looked at earlier on, just trying to go back and find those. So these pulleys here, the one on the left and the one on the right, they were on a turnover conveyor. That wear was occurring inside of 3 months and was causing serious problems. We changed that lagging to a polyurethane lagging, and basically that lagging lasted for 3 years. So we went from 3 months to 3 years by going to polyurethane. Now, I don't think that was just due to abrasion resistance. If the lagging had been put on here, had been the extreme rubber, we would not have got 3 years. It was the combination of the much better abrasion resistance and the low surface energy, so that the shear stresses that were occurring from the contact with the belt, it was able to slide on the polyurethane. Now, if you just look up at the top of the belt here, I don't know if you can see this, but leaving this problem, this wear problem, not doing anything about it, you can see what it's been doing to the belt. It's actually worn through the bottom cover and exposed the cords. So the problem shows up in the lagging first because you've got much smaller surface area. But if you don't do something about it, it'll eventually turn up in the belts as well. Just let me go back to where we were. Okay. The next failure mode that we'll look at is tile breakage, which you can see in these three photos. Quite severe tile breakage. Tile breakage is due to material being trapped between the belt and the pulley shell, and look, this can be difficult to completely eliminate in operation. There are things that you can do with the lagging that will reduce the tile breakage, and these are. So as a lagging, when you're manufacturing lagging, 80% of the material cost in ceramic lagging is in the ceramic tiles. So the way that you make a low-cost ceramic lagging is you buy low-cost ceramic tiles. So if you look at these two photos, they look identical. This tile on the left is a tile that you could buy. This is a standard tile used in ceramic lagging. It's 20 by 20 by roughly 5 millimeters thick. And that tile you could buy for 2 US cents each. And if you did a Vickers hardness measurement on it, you would get around about 600. The tile on the right, same size tile. If you were to hold these two tiles in your hand, you would not be able to visually tell the difference. It has a Vickers hardness of 980, but it'll cost you 5 cents. So 2.5 times. And you can't get away from this. This is just the reality. People that want to make low-cost ceramic lagging will more than likely be buying low-cost tiles because they're buying a cheaper tile. It's made from a material that's been filled, and The downside in operation is that the dimples will break off. You can actually have dimpled lagging and find where it's almost smooth because the dimples have just gone. You know, they've just been removed. You can actually also wear through these ceramic tiles. Very, very important when you're looking at ceramic lagging. If you want to specify or choose something, that you need to at least find out the quality of the ceramic that's being used. So another thing that can help you minimize the chances of tile breakage is the thickness of the tiles. So we look at the cracking force, and we've got two tiles here. This is the 20 by 20 by 5 mil tile. This is a 20 by 20 by 8 mil tile. If we look at the force required to break these tiles, I'll just show you how we do this test. So this machine here, we put the tile in little jigs so that the tile is held on each side. And then this plunger comes down and applies a load to the center of the tile. And we measure the force that's required to crack the tile. Now, a 5 millimeter tile will crack with 2,000 to 3,000 newtons of force. The 10 millimeter tile, our machine tops out at 10,000 newtons, so we can't crack those tiles. So by going from 5 mil to 10 mil, we've increased the crack resistance more than 300%. We also have thicker tiles again. Needless to say, we haven't been able to test those. When you do use thicker tiles, they have to go in thicker rubber. So, for example, you can't put a 10 mil tile and make 12 mil lagging, have 2 mil of rubber on the back. Basically, if you're using the 5 mil tiles in your 12 millimeter lagging and you're getting cracking and you want to reduce it, you go to the thicker tile, but you're going to end up going to a 20 or a 25 mil thick lagging so that you've got rubber behind the tile to help cushion it and combine with the increased crack resistance. The third thing that you can do is put a cushion of rubber between the tiles. You will have seen that there are ceramic, and I'm talking now about the full ceramic, the 80% ceramic. You'll see that there are versions where the tiles are touching each other. The problem with that design is that when you get material caught in between the belt and the lagging, it point loads onto the tiles, and if the tiles are touching each other, there's basically nowhere for things to move. There's no cushioning, and ceramic is inherently brittle, so you just increase the likelihood that those point loads will actually fracture the tiles. The thinking behind putting 2 to 3 mil of rubber between each tile is that it provides some cushioning. Some cushioning from those point loads, and it helps to reduce the chance of breakage. An added bonus is that by having rubber on the sides as well as the back, you increase the bonded surface area. You don't double it, but it's nearly double the bonded surface area. So it's just an added bonus. So just in summary, ways to minimize tile breakage. Make sure you've got good quality tiles with high hardness, increase the tile thickness, and then look at lagging designs where the ceramic tiles have rubber on the back and around the sides. The last form of failure mode that we will look at is lagging fatigue. You can see these photos that they are all rubber lagging, but you can get lagging fatigue on ceramic lagging. Basically, this is where the shear forces that are being applied to the lagging in a cyclic fashion as the pulley's rotating basically exceed the fatigue life of the rubber. What you can do, or the best way to prevent this or find a solution if it occurs is to do the lagging analyst analysis. So this lagging on the left, this is a real case that occurred at a large mine in Australia, where this lagging failed within 4 weeks. You can see the large diamonds have basically been completely removed and the small diamonds are very badly damaged. This is the lagging select analysis. So the black line is the operational line. This is where the belt first contacts the lagging. This is the exit point over here. So this orange line here is the tread route limit. And you can see the operational black line is well above the tread route limit. So that's basically telling us, it's saying, look, this lagging is going to fail due to fatigue. Fatigue at the tread route limit, that's exactly what's happened. When this problem occurred, we had to find a lagging to be used. The mine site did not want to use ceramic lagging. They were concerned about putting ceramic lagging on and transferring the damage from the lagging to the belt. The belt was $6 million and had a 6-month lead time, so they definitely didn't want to damage the belt. So in the analysis, we analysed a whole range of different types of laggings. The one that came up with the best result was this herringbone design. This is the graphical printout. You can see here this black operational line has moved down. You know, it's moved from up here where it was, it's moved down. It's partially in the green zone. This is the orange line is the tread route limit. It's partially in the green zone, so it's right on the limit. So the limit we're using for fatigue life is 5 years. So effectively what this is saying is that you're right on the limit, and it may not get to the 5 years. Now in practice, that lagging was installed in October 2021 and it lasted for about 3 years before it required replacing. So the one on the left, 4 weeks, and this one on the right, 3 years. So there's ongoing work to try and come up with something that's going to last even longer, because these bearings last a lot longer than 3 years. So 3 years is not really satisfactory. Now, the last thing that we'll look at is spare pulleys. Often when you have spare pulleys, they have to be used to cover more than one location. This is just an example of a conveyor layout for a gearless drive pulley. We've got two drive pulleys here, primary and a secondary drive, head pulley, tail pulley, and then multiple other pulleys. So we could have, say, for example, on the non-drive side, we could have pulleys that need to handle both dirty side of the belt and clean side. Often with spare pulleys, people put the cheapest lagging on. If that's what happens and the pulley then gets put into a situation where it's dealing with the dirty side of the belt, it means that the lagging will fail more quickly than it should. So our recommendation is that when you're looking at a spare pulley, look at the worst location that it might have to go, and then select the lagging that you would give you the optimum performance in that worst location. That way, you know, if the pulley has to go into one of the other locations, it's going to perform really, really well. And if it has to go into the location that's the most difficult, it should still perform as well as could be expected. That's basically it for me. If there are any questions, I'd be happy to try and answer them. I don't know if there are any questions in the chat.
So, thank you, David, for the presentation. I have one question about the surface energy. I don't really understand what's that, how you measure that, and what's the number shows us. What is this surface energy?
Surface energy is, I think from memory, Adam, it's dynes per centimeter, and it's measured. Surface energy is measured using a machine called a. You have to excuse my pronunciation. It's called a goniometer. It's basically you take the surface that you want to measure, and you put a droplet of a liquid. Usually it's you might start off with water. If it's something like Teflon, you'll get a bead, and you measure the angle of contact.
Okay.
If you can't measure that, then another technique they use is they have different liquids. So you might have a range of different oils. You might have water, you might have some solvents, and they come as standard liquids with known surface energies, and you put them on the surface that you're trying to measure. If they wet out, then you know that the surface energy of your surface is higher, and you just keep putting on the different liquids until you get one that balls up, and then that gives you a rough idea of what the surface energy is. But the goniometer is the way that they do the actual measurements of surface energy.
So the ceramic has pretty high surface energy according to your measurements. But
yes,
if it's smooth tiles, there are smooth tiles. They could be very smooth, and if they run, they are polished and they are pretty smooth, I think. But
yeah, if you polish something, the surface energy, I think that would make the surface energy lower. But the problem with ceramics is that it's a very granular structure. So when you have a granular structure, it's much harder to get a low surface energy than if you have what I'd call a polymeric structure, like a plastic or a paint film or an epoxy. That's a non-granular structure. Are you looking to try and get a ceramic that has good release properties?
yeah, because ceramic, there's smooth ceramic. There are smooth plates without these dimples and not dimpled, and maybe they are better. And what about the grooving? Is grooving improving this resistance against material build-up, or because if you have more surface, how is it?
So grooving helps when you have a flexible lagging, because it allows the lagging to move, and if the lagging can flex, it makes it more difficult for things to stick to it. Grooving on rigid lagging like direct bond won't aid the release properties. All that does is maybe give you some water shedding ability. Does that answer your question?
Yes. Thank you.
No problem.
Good question, David. Have you had much to do with polyurethane pulleys?
We manufacture a polyurethane lagging, so I have experience with rubber back polyurethanes. I don't have any direct experience with hot cast polyurethane, Rion.
Okay, cool. Might reach out offline and have a chat about it.
No, that'd be good. Any other questions? I couldn't see if we had any in the chat or not.
In regard to the fatigue properties or life of the lagging, is that 5 years and 60 RPM, 24/7, whatever? Is that just some sort of arbitrary figure you use to base it on, or can you get a larger fatigue life, as you were saying, longer than the bearings and so forth, if chosen properly and you don't run into slip and other things?
Yeah, Rick, we just picked that. The development of that lagging select software tool was done in conjunction with Conveyor Dynamics in the US, and we just had to pick an arbitrary figure as a benchmark for the fatigue. So when this was all being done for the lagging failure that we were investigating. That site operates 24 hours a day, 7 days a week. So, and they were operating at 60 RPM. So we just arbitrarily said, okay, 5 years, and we worked out the number of cycles, and then we had the data on the rubber properties to work out the fatigue life of the rubber, and so we just picked that as an arbitrary figure.
And so obviously the aim is to try and stay below that if you want improved life. Do you suffer in the very long term from actual degradation of the rubber in any way? Like tyres obviously don't stay fresh forever. Do you actually have issues further down the track? As you say, if you're trying to outlast your bearings and other things, does the actual life of the lagging eventually go downhill regardless?
Yeah, lagging rubber ages. So, for example, you see a lot of mine sites and they have their spare pulleys and they stick them outside. They're sitting outside,
Yep,
in a
out in the
wooden
sun
crate or out in the sun and all the rest of it. So the things that degrade rubber are heat and UV. So if you were, if you had like a pulley, a new pulley, and you put lagging on it and you put it into service, and we've done the lagging select calculations, the 5-year service life, you'll get a different result if you take that same pulley and you stick it out in a spares yard for 5 years in the sun and the weather and all the rest of it, and then you take that pulley and you put it on the conveyor. That's a whole different ball of wax.
Yep.
Additionally, we are finding that on some very high-powered conveyors, like we've done quite a bit of work with Chuquicamata. They're running ST10,000, and I think it's a 6-megawatt drive. That particular environment, the very high shear loading that's being and power transfer that the rubber's being subjected to, is actually changing the makeup of the rubber. So all the things we're doing are based on new lagging, new pulley, and it's like a theoretical baseline. And as soon as the pulley's older or the lagging's been stored a different way, or it's, special circumstances where you're dealing with very high powers, it all becomes a special case and a bit different.
Yep. Thanks very much.
So which lagging did you propose for Chuquicamata for this is the 10,000?
That's got the extreme rubber lagging.
Mm-hmm. For the drive pulleys as well?
Yes, yeah, for the drive pulleys. That's for basically the combination of very good abrasion resistance. It's got very good physical properties and heat resistance, and good release properties, because that particular pulley is operating in very dirty conditions. I think there might be
one.
Sorry,
I have
Adam,
one
go
question more. In the slide 28, you showed that there's some measurements about different laggings, and there is a measurement of abrasion resistance for direct bond full ceramic lagging. Is it really? Can you really measure it on the same test bench as a rubber? Because I somehow don't believe you can compare that with the same number. Yeah.
No, you can't. That's just an arbitrary number that's put in there just to basically indicate that ceramic is very, very low. If you were to make, you could make a cylindrical plug and put it on that test, and I think the result would probably be almost zero.
Exactly, I think the same.
Yeah, we haven't physically done the test. It's really just to indicate that on that type of test, the result would be almost nil.
Mm-hmm.
There is a question from Stephen, which is for applications where the lagging has direct contact with the material on the top side of the belt. We could also look at installing a belt wash station to clean the material from the belt before it meets the pulley. Then you also have to cost to install a launder to catch the water. Yeah, that's true. That's 100% correct, Stephen. Anything you can do to keep the belt clean makes a huge difference to lagging life for pulleys contacting the dirty side. All right. Any more questions?
I have one last question, maybe. In the first analysis of the drive pulley, there are some different leggings compared, but not polyurethane. And you showed polyurethane had pretty good properties against fatigue. Is it not? You don't recommend it for drive pulleys, or why didn't you consider it in the first drive pulley comparison?
We, Adam, we haven't done any work on polyurethane for drive pulleys. Polyurethane is used for drive pulleys, and particular area where it's used quite commonly is the oil sands in Canada. They use polyurethane because of the combination of abrasion resistance, release, and release properties. For us, for drive pulleys where we want that extra abrasion resistance, we use the extreme rubber because we like the flexibility. We like the fact that the rubber can flex with the belt. We think it's kinder to the belt with polyurethane, and it's got similar abrasion. So that's the reason we've gone down that path. But there are people using hot cast polyurethane on drive.
That also be to be compatible with the tar and the oil sands and that? That would degrade your rubber, I would have thought.
Correct. We couldn't use the extreme rubber and the oil sands because it's not oil resistant. It would just get destroyed. The polyurethane has the oil. I should have mentioned it has the oil resistance as well. There's one more question here. Could we get advice for a drive pulley that's used in fertilizer, where the pulleys slip when it's wet due to rain and the material is sticking? The customer chooses to use 80% ceramic coverage. Is that good or not good?